Okay, that's the span of F1, F2, F3, F4, where F1 is -1, 1, 0, F2 is 0, 1, 2, F3 is 1, 0, -1, and F4 is 2, 1, 3. A. Find the basis B1 of W. B. Write the change of base matrix from B0 to B1, where B0 is the basis of R3, is a basis of R3. Find the change of basis matrices from B0 to B2, B1 to B2, B2 to B1, and the last point, let V equals 3, 2, 7 be a vector written with respect to B1. Find the coordinates of V with respect to B2. Janan, do you mean that you want to solve such a problem?
Yes, this type of problem.
Okay. Let's start. Let's see. I will let you 2 minutes to find the basis of Have you found the basis? So let's see, the basis is formed with?
The vectors f1, f2, and f3, for example.
Okay, indeed. Because if you write the matrix that contains f1, f2, f3, and f4, and if you rank, you will see that the rank is equal to
3.
3, exactly. So here you write f1, I'm going to write them f2, take the term here, it's not 0. So the rank of A is 3. So f1, f2, and f3 divided by b is 3. Okay, so we have found the basis. Then you have to write the change of basis matrix from B0 to B1, where B0 is the canonical basis of R3. Okay, I will let you 2 minutes to write B0 and then to write the matrix from B0 to B1. So, have you found the matrix or not?
I have a little bit of computation to make, and I will find it.
Just a second. What computations?
So we have to find f1 to express in by e1, e2, and e3, and
Yes,
then we will put the coefficients we found on the columns of the matrix.
exactly. But what computation do you have to do?
So I find only the first element. I have the other two to find.
Just a second. You already know them. You don't need to make computations here. So in order to find this matrix, you have to write F1, F2, and F3 as you have here. This is F2 and F3 using E1, E2, and E3. So you have to find A1, A2, A3, then B1, B2, B3, and then C1, C2, and C3, such that F1 is this vector, F3 is this vector, F3 is this vector. And then to A1, A2, A3, B1, B2, B3, and C1, C2, C3. I will start making the computations to show that there is no need to make any type of computations here. So let's take a look at F1. So let's say that this is 1. Okay, let's take a look at 1. You have that F1, which is minus 1, 1, 0, must be written as A1 times 1, 0, 0, plus 2 times 0, 1, 0, plus A3 times 0, 0, 1. So you have that this is equivalent with minus 1, 1, 0 equals, and when you make the sum, you get what?
Minus E1 plus minus 1, 0, 0.
No, here, when you make the sum, you get A1 on the first position, right?
Yes, A1, A2, A3.
A3. So, actually, the first column of this matrix is who?
Minus
Who
1,
is
1,
this
0.
column? Yes. So, actually, the first column of this matrix is what vector? B2, B3.
Will be F2,
Okay, this one will be
F3.
F3. So, your matrix C0B1 will be equal to what? Part of the matrix A. With the first 3 columns. So you have to write F1 here, then F2, and then F3. And that's all. Okay, this is F2, and this is F3. Okay, going to write it. So to computations, you could write directly this matrix. Okay, you write it and that's all. So the solution of B consists of this line and this matrix, and that's all. You don't need computations. Okay?
Yes.
Very well. Let's move to point C. Is B2 a basis of R3? Check this. Okay, so I'll give you 2 minutes to check B2 is a basis of R3.
Okay, so the vectors in the set are linearly independent
Yes.
because it's with the determinant, and the dimension of the subspace is 3, which is the dimension of R3. So B2 is the basis.
This is the idea. So you have that B2 is a basis of R3, and let me write it first. And then you have to find these matrices, but let me write the idea that you have told me. Let's denote this one by G1, okay, this one by G2, and this one by G3. Oh, so I'm going to see you have to write the matrix with G1, G2, and G3 to see that this determinant is not zero. So it means that B2 is a linearly independent system. And because B2 is 3 and the version of 3 is 3, and in B2 has 3 vectors, it means that 2 is the basis of R3. Okay, so you have a basis, and you have finished solving C. Let's move to point D. You have to find the change of basis matrix first from B0 to B2. Okay, so I'm going to write here first C, B0, B2. And I will let you 1 minute to write this matrix C, B0, B2. I'll put this to
Yes, the matrix is G1, G2, G3 right on the columns.
same idea which you have seen at the point B. Okay, so because B0 is the canonical basis, this matrix is actually the matrix with G1, G2, and G3 here. Okay, well, let me write the matrix. C1, 2. I want you to find this matrix. Tell me, what do you have to do in order to find this matrix?
So we have to compute CB1 B0 multiplied by C B0 B2.
Yes, this is a very good method for finding this matrix. Another method is based on this one. So you have to find the coefficients A1, A2, and 3, and so on, such that G1 will be A1 F1 plus A2 F2 plus A3 F3. But this method will take lots of time because actually you have to solve three systems, each having three equations. So my advice is to use what you have told me here, Jana, and this is based on the matrix which contains B0 here. So the idea is that if you want to go from B1 to B2, then you have to go first to B0 and then to move to B2. And from here to here, you have the matrix C, B1, B0. Okay, let me write better. So, so C, B0, and this is C, B1, B0, and this is C, B0, B2. And if you want to go from here, then you have to use the matrix C, B1, B2. So it means that the matrix C, B1, B2 is actually C, B1, B0 times C, B0, B2. Oh, you know C, B0, B2, you have this matrix here. But how do you find C, B1, B0?
Is the inverse of CB0 B1.
Exactly, it's C, B0, B1 at minus 1. So from these two facts, you have that C, B1 is actually C0, B1 minus 1 times C0. You have to use the quantity to find the values. Do you manage to find the values? Do you manage to find the inverse of the matrix of CB0, B1?
Just a little bit. Finish.
Can you repeat this?
Just a little bit to finish, and I will tell the inverse.
Okay, I'm waiting.
Okay, so the inverse of this matrix is minus 1 over 3, 2 over 3, minus 1 over 3.
Then,
1 over 3,
okay,
2 over 3, 2 over 3, 1 over 3, 2 over 3, minus 1 over 3, 1 over 3, and again minus 1 over 3.
okay, this is the inverse. You have that C, B0, B1 is
Minus 1,
Yes.
1, 0,
Okay.
0, 1, 2,
And
1, 0, minus 1.
let's see. 0, minus 1. Yeah. Okay. And if you multiply them, do you have the matrix with 1 on the main diagonal and then 0? Let's check. So you have this one times this one is minus 1 over 3, which is 1 over 3 times this one, plus 2 over 3 is 1. Then this line times this line gives you 2 over 3 minus 2 over 3, which is 0. This one times this one plus this one times this one times this one is 1. So 0, so because you have minus and then plus, so it's fine, it's 0 here. Okay, and then you have 0 and 1 and 0 and 0 and 0 and okay, that's perfect. So this is the first. Fine. Well computed. Okay, so see, 1 minus 1 is this one, and then you have to multiply this matrix. CB2, B2, which is this one. Okay, see the computations. So you have minus 2 over 3 plus 2 over 3 minus 1 over 3 is minus 1 over 3. 2 over 3 minus 3 is minus 1 again. You have 1 over 3 minus 4 over 3 is minus 3 over 3, which is minus 1. Then 2 over 3, 4 over 3. 4 over 3 and 1. Minus 2 over 3 and minus 4 is minus 6, so is minus 2. Okay, is this the matrix? Are the computations correct?
Yes.
Okay. So this is CB1, B2. And we have one more matrix to find, right? We have this one, CB2, B1. How do you find CB2, B1?
So will be C B2 B0 multiplied by C B0 B1.
Yes, but make advanced computations, I should use this matrix.
Oh yeah, yes. It's the inverse of C B2 B1.
Exactly. It's this one. Okay, so you have to find the inverse of this matrix and you get the result. This is your homework. And we have a point here, the point E, which tells you to find the coordinates of E with respect to B2. So let's So let's get the point E. You have a vector v, and note that the coordinates of v with respect to b1 are 3, 2, 7, okay? They are the coordinates with respect to b1, 3 to 7. So I'm going to write in this way, 3 to 7, and I'm going to write the vector using y. And I have to find the coordinates of v with respect to b2. You know that the coordinates of v with respect to b2 are given by the change of basis matrix from b2 to b1 times the coordinates of v with respect to b1. This is the matrix which is actually C b1 b2 at -1, so it's the inverse of this one. And because we haven't computed this matrix, I'm going to write in this way. So I have a matrix with 3 lines and 3 columns. I don't know. And let's multiply this vector. And this is why I have written the vector as a column, because if I want to multiply such a matrix by such a vector, I have to write it on the column. Okay, and then you have to make the multiplications, and you'll get a vector which will have, again, 3 lines and 1 column. And this vector will be give the so with respect to b2. And so So, then if you have questions, do you have questions
Now it's clear.
for okay, other questions? Then what other questions do you have? If you don't have other questions, I can suggest you a problem. But tell me first if you want to ask me something else from the seminar or from the course. Okay, so if you don't have other questions, um, I'm going to write another problem. Let me with the same x plus 2, x minus 3, x cubed plus 1, x cubed plus x minus 2. And this is a subset of R3 of x. A. Find W, which is the span of E, and dimension of W, of course, over R. B. Could the basis of W be completed to a basis in R3? if complex. C. Find the D. Let B be the basis of W. Unite the basis of W prime. Be a basis of R3 of X. Orthonormal. And here you have that R3 of X is the space of all the polynomials with degree at most 3. And that product between two polynomials P and Q will give you the product of the coefficients. So it will be P3, Q3 plus P2, Q2 plus P1, Q1 plus P0, Q2 plus P0 and for any B and Q in 3. Okay, see the product. I need 2.8 Have you solved point A? Have you solved the first point? Or did you have to do this in solving A?
I have a question. I don't remember. First of all, to prove that V is a spin of W is a span of E, you have to rewrite the vectors from E.
Yes, but you don't know who is W. This is just notation.
Oh,
So you have to put that is the span of E because you don't know who is that. I've told you that we denote by W the span of E. Okay, and
okay.
you have to find W. And what you should do?
We have to express the vectors from E by to find a relation. Let's say constant multiplied by a vector.
Yes, so actually, if you denote, let's say, by P1, not P1, because P1 is the notation for the coefficient. Okay, let's say P R S and D. Let's say capital R, capital S, capital T, capital P, and the small q. So we have five polynomials. Going to write P, Q, R, S, and T. Okay, we have five polynomials. You want to find the span. So you have to use, of course, definition of the span. A span is defined by the space of all the linear combinations, which can be written using the elements of the set E. So in this case, span of E is that which is in this way. It is, let's say, A times B plus B times Q plus C times R plus D times S plus E times D, where A, B, C, D, E are and P, Q, S T are the polynomials written here. But you have here a lot of polynomials. And this span is actually a subset of R3 of X. You know that the dimension of R3 of X is
4.
what? Is 4, exactly. So having here five polynomials, it means that you cannot have all the polynomials linearly independent because they are more than the dimension of this space. So in order to find easily the span, I'm going to extract from here only the polynomials which are independent. And in this way, I will find also the dimension of this space W. Okay, so point is point the polynomials which are independent. So if P R S nearly independent, we have seen that the answer is no. So let's extract from here a linearly independent set. How do you do this extraction?
So we put the vectors of the column, see find the, let's say, four vectors linearly independent, and the other one will be dependent, so we'll extract it.
Okay, but in this case, you don't have vectors from R3. How do you find them in columns?
How do you find the columns?
Yes,
So on the columns, we'll put the coefficients of the polynomials.
exactly. You have to think that this is 0 times x squared, x cubed, sorry, plus times x squared, plus 0 times x, plus 0x, plus 1 times 1. So actually, this will correspond to 0, 0, 0, 0, 1, but written on a column. Sorry, 0, 0, I've written this twice. Sorry. I was thinking at R4. Okay, so this is the vector. Then for this one, you have what vector?
0, 0, 1, 2.
Exactly. For this one, you have
It's 0, 0, 1, minus 3.
effect. For this one, you have
1, 0, 0, 1.
x, and this one is
1, 0, 1, minus 2.
this. So we write the matrix denoted by say, which contains these vectors, but written on the column. Okay. On each column, I have a vector. And please explore from here as linearly independent vectors. Yeah.
We cannot extract linear independent vectors from here. Only.
How?
So if you take like the first four, we cannot get the maximum rank because we have the line with zeros. And if you
Yes,
take any four vectors taken from there, will be zero the determinant.
exactly. Actually, you should think it this way. You should look at the polynomials and notice that R can be written as a linearly combination of P and Q. Actually, R from here is Q plus minus 5 times P, right?
Yes.
Because if you compute this one minus 5 times this one, you get R. So it is clear that the third line, the column, the third column is a linearly combination of the first one and the second one. So this one. So you have that this won't be in your system of linearly independent vectors. So you have to cut this column. And also, if you take a look at S, T, and P, could you write T using P and S, or using P and S? Well, here means S plus Q, correct?
Yes.
So if you add s and q, you have x cubed plus x plus 3. And you have a minus 5 plus minus 5 times this one, times b. So t could be written using s, q, and b. So it means that t will also become from here. Okay? T disappears from here. So actually, you have one linear independent polynomial.
Only the first, second, and fourth polynomials are linearly independent.
Yes. So if you write again the matrix with these polynomials, you will see that the rank of this matrix is
So,
not actually. Let's try this. Okay, because you are right of V exposed and work with columns. So in this case, the rank of B
3.
is 3 because the minor which is not 0 is this one 0 0 1 0 1 0 1 2 1. Okay, this is not 0. So the rank of B is 3. So it means that P, Q, and S are linked in fact. And because they are independent, it means that this span could be written using only P, Q, and S. Okay, I cut from here R and T. I'm not going to use them. So it means that W, which is span of E, is the span of P, Q, and S. So it is A times P plus P times Q plus C times S with C in R. So it actually times 1 plus P times Q was X plus 2 plus C times X cubed plus 1. ABC in R. So it is cx cubed from here plus x from here plus a plus 2b plus c. Okay, so this is W. And what's the dimension of it?
It's 4.
What?
Because we have a polynomial from R3.
Actually, you have a polynomial which is generated by p, q, and s.
Oh, so the dimension is 3.
Yes, the dimension is 3 because p, q, and s is a generating system for W. And P, Q, and S is a linearly independent system. So P, Q, S is basis in W. dimension 3 because you don't have x squared here. Could you tell me, please, another basis of W? Another basis has well, you should write W plus alpha times x squared, where alpha is c, plus beta times x, right? Plus, and here which is not this one or this one. So this is something else, which is totally different from C and B. So you have plus gamma with alpha, beta, gamma in R. So actually, W could be seen as the span of x squared, x, and 1 from here. And because x, not x squared, x cubed, x and 1 is linearly independent, you have that x cubed, x, and 1 is a basis of W. Okay, this is another basis. But this was just, is it clear or no?
We can see this observation like the basis. This was a basis in W from the first.
Can you repeat, please?
So we can denote with alpha, beta, and gamma from the start when you
Yes,
write the span.
yes. If you want from here, you should write that this is alpha, this is a beta, and this is something else. Because if you had here just to B plus C, then this won't be gamma. This will be to alpha plus beta, but because you have here this A, it means that actually you have here a different value from this ones. So you have a gamma and you could use this basis from the beginning, yes.
Okay.
On this point A, let's suppose the basis of that be completed up to a basis in R3 of X? If so, complete it. Could you complete this basis? So let's say that this is BW, and let's say that this is prime. Let's work with both of them. Could you complete this basis to a basis of R3 of X?
Yes, we can take a vector from the canonical base, and I think will be completed.
If you have PQS here with X plus 2 and X cubed plus 1, and you want to choose what from the canonical basis?
Let's say the one with x squared because it's not here.
Exactly. If you take 1x plus 2x cubed plus 1 and x squared. So you add this a basis of r of x, and your homework is to justify why. And how would you justify this as a basis?
So we computed it. We'll make the same with putting on the columns. We computed the determinant and the rank. We will see
Yes,
like the rank will be 4, and then
yes,
the dimension is uh, as well 4 as the
exactly.
R3, and that's it.
Oh, that's perfect. Let's think of double prime, which consists of 1, x, and x cubed. This could be also completed to a basis of R3 of x by adding what to this basis?
We'll add the expert.
Exactly. We have the square, and this is the canonical basis of R3 of x.
I have a question. When we add a vector to a set, it's important his order. Let's
No,
say,
no,
oh, okay.
the order is not important because you have a set in which you could write the elements in each order you want. Okay, so it is not important. Let's see point C. Let's see point C. Find the perpendicular. Okay, so W is this space. I'm going to come here again. This is W for this one. Please find W perpendicular, where by doing a product, I mean the product of the coefficients and the sum of these results. I have 5 minutes to find W perpendicular. found perpendicular.
Yes, so we take a vector, let's say x, y, z, and t.
Okay. So this is a vector which is not actually x, y, z because we must write a polynomial. The vectors are polynomials here.
It's like,
The,
let's
uh,
say, alpha.
okay, okay, or alpha, yes. Just a second. Alpha cubed plus beta plus c plus delta plus x.
It's a mistake. You wrote x times.
Sorry. I'm thinking again about R4. I don't know. Initially, I was thinking about an example with R4, and this is why in my mind the polynomial must have five coefficients instead of four. Okay, let's say epsilon instead of delta. So I have alpha, beta, gamma, epsilon in R. Thank you. Okay, and what is the condition that you have to write? So let's say that it is zero. Is
Okay, so the inner product between this vector and all the vectors from W need to be zero.
yes.
And
Uh,
you build a system of equation and then solve it.
exactly. But that, that right this way. So right here, all the conditions to be more clear. So you have that Z and B equal zero. Also, Z and Q in that product is zero. And Z and S, right? In that product is zero. Okay, and let's take each condition at a time. So you have this one equals zero, but B is one.
Yeah, and you get
And
from there epsilon is zero.
exactly, because it is times zero plus beta times zero plus gamma times zero plus epsilon is zero. So you get exact that epsilon is zero. Then Z and Q is zero where Q is x plus one. So you get that.
Gamma plus epsilon equals zero, so epsilon is zero, gamma is zero.
Exactly. So gamma plus epsilon is zero. So actually gamma is zero. And from the last condition, this is x cubed plus 1. You get?
Alpha zero.
Yes, because this is alpha times 1 plus beta times 0 plus gamma times 0 plus epsilon times 1 is 0. Okay, so you get that alpha plus epsilon is 0, but epsilon is 0, so alpha is 0. So actually, W perpendicular consists of what polynomials?
Beta x squared.
Exactly. W perpendicular is beta x squared with beta in R. Okay, and this was point C. Let's go to point D. We have D, the relation between a basis of W and a basis of W perpendicular, which will be, of course, a basis of R3 of X, and we want to orthonorm B. Okay, so let's see what we have until now. Just a second. So we that B the basis of W, consists of P, Q, and S. Okay, and this is a basis of double. Or we could take BW prime, which consists of 1x and x cubed. Again, the basis of. And do you have basis of the perpendicular?
Yes, the basis is x squared.
Okay, and this is basis of double perpendicular. So we have two methods of, there are not two methods, there are two cases. So case one, we choose B to be BW in reunion with BW perpendicular, which is P, actually 1, right? Q, which is x plus 2, S, which is x cubed plus 1, and then x squared. And you have orthogonal bases. And case 2, let's say B prime, which is BW prime reunited with BW perpendicular, which is x, x cubed, and x squared. Which base is easier to orthonorm?
The second one
Exactly. Actually, what kind of basis do we have here?
is the canonical basis.
Yeah. And how are the polynomials in this basis? Are they orthogonal?
Yes, are they orthogonal? Oh,
So,
no,
yes or no?
no, it's yes.
It's
They
yes,
are
because one and x is
it's 0, it's 1 more multiplied by 0 plus 0, 0, so on.
1 x cubed is 0, x squared is 0, and then x cubed is 0, x, x squared is 0, and x cubed, x squared is 0. Okay, so it means that prime is orthogonal. But do the vectors from here the norm 1? Let's find the norm of 1, this polynomial. The norm of 1 means the square root from the dot product of 1 with 1, which is,
1.
okay, it's perfect. Norm of x is
1 as well.
exactly x. So it's 1, again, norm of x squared is 1, and x cubed is 1. So prime is already orthogonal. Okay, let's see case 1 because case 2, it was a simple case. Okay, let's see case 1. I will let you 10 minutes to find the orthogonal basis starting from this basis B, and you have to use the Gram-Schmidt procedure, but first try to rearrange those vectors, these vectors, I'm sorry. My internet connection is so bad. Okay, so if you want to orthonorm these bases, first you have to orthogonalize these bases and choose the vectors from here such that it's easier to apply Gram-Schmidt. For example, the first vector will be this one, but choose the second vector to be something which is perpendicular on one.
We can see. Sorry,
So do you,
it's not share screen.
oh, sorry. Sorry. So the first vector to be 1, and then to choose another vector which is perpendicular on 1 to be easier for you. So the second vector would be chosen as
X.
something from this set. Do you hear something which is perpendicular on 1?
Yes, you
That
can choose
is the
any of other of them. So you can choose X square, for example.
yes, but not any of them, just x squared because this is perpendicular on 1. Just 1.
And why is not? Oh yes, because we have X plus 2 and X3 plus 1.
Yes,
Yes,
you have 2 times
makes
1
sense.
here.
Yes, makes sense.
So in this case, you could choose this one to being x squared. And if you want to construct F3, you take it as, let's say this was P, this was Q, this was S, and this is, it doesn't matter, this is F2. This is P, let's say this is, but this will be F2. Okay, so you have this one as Q minus the projection of Q onto F1 minus the projection of Q onto F2. Okay, because this is actually P and this is actually Z. So I'm working now with Q. After F4, I have this one, which is S. So I have S minus the projection of S onto F1 minus the projection of S onto F2 minus the projection of S onto F3. How do you compute F3?
So we copy the projections and then
Yes, and it's actually Q1 over F1 times F1 and Q was x plus 2 and x was x squared x cubed plus. So this is Q divided with F1, which will be equal to Q with F1.
1. Oh, no. It will be 2.
2 over 1, this is 1, times F1, which is 1, so this is 2. Okay, and the projection of Q onto F2 will be Q F2 over F2 times F2. So F2 is Q, this is F2.
It's 1.
Uh,
No, no, it's not 1. It's 0.
yes, it doesn't matter. It's F2, so it's 0. Okay, so it implies that F3 is Q, which is x plus 2, minus the projection of Q onto F1, which is 2. F3 Have you finished the computations?
Yes, f4 it's x cubed.
Exactly. F4 cubed. So actually, the basis that you get is 1 x squared x and x cubed, which is an orthonormed basis. And that's all. So you get the same basis as you have in case 2. Okay, do you have questions?
Okay, so if you write like in the first, we get like 1 x squared x and x cubed. We don't have to make either computations. You just or you have to take the two cases.
If you use this, it has to prove that having diagonal and so on for each of them. And you get the result. And that's all.
Oh, okay.
But I want to discuss both of them to see how to do computations.
Okay.
Other question. If you don't have a question, then let's take a minute to download the attendance list and to check the attendance list. Okay. Popescu Emanuel, are you here?
Yes, I'm here.
Perfect. With John, I helped a lot. Secretary, here.
I'm here.
Okay. Down it.
Yes.
And Rusa Alexandra?
Yes, I'm here.
Okay, that's perfect. Do you have questions? Okay, if not, thank you for attention. Have a nice day and have a nice week too. Goodbye.
Goodbye. Have a nice day.
Goodbye.
Goodbye.
Thank you.
Bye. Have a nice day.
Thank you.